Alright, this is the final topic of Chapter 2, the kinematics of free fall. So we're still talking about one-dimensional motion, but now we're talking about freely falling objects. And what are they? Those are objects that are in the air near the surface of the Earth, and they're only under the influence of gravity. So any object that's in the air close to the surface of the Earth is going to accelerate in the negative y direction. So, you know, what comes up must come down, right? So every object in the air is going to accelerate towards the surface of the Earth. So our coordinate system is going to follow the convention that anything that is traveling up in the air away from the surface of the Earth is the positive y direction, and down towards the center, or down towards the surface of the Earth, is going to be the negative y direction. So if you ever had high school physics, you know, maybe your instructor might have flipped it around just to kind of get rid of negative signs and make their lives easier or something like that. But we're going to stick with this convention. Up is positive, down is negative. So we're going to ignore what we call drag. So that's the air resistance. Any object you know, that's in the Earth's atmosphere is subject to air resistance. So we're going to neglect that. And so the acceleration due to gravity is 9.8 meters per second squared in the negative y direction. So I'm going to go through the equations, and then we'll talk about how we handle the direction of g. I know, you know, some people kind of do it differently, but there's a negative sign issue with our kinematics equations that can kind of get us confused and lead to some errors. So I'm going to show you how I handle free fall. I'll modify the kinematics equations. I'll account for the direction of the object's acceleration vector. I think my way is the easiest. Hopefully you'll see the process and agree with me. If not, you know, obviously, you know, we can handle the situations as long as it's correct. But like I said, I'm just going to show you how I like to handle free fall kinematics. Okay, we've got three cases. I'm going to split free fall kinematics problems into three cases. So these are the first two cases. Let's say I'm on top of a building, right, or on top of scaffolding or something like that, and I've got an object. I've got a ball or a brick or something like that. So I can do two things with that object, right? I'm some height above the surface of the Earth. I can do two things with that object. I can just let go of it and I can drop it, or I can throw it down, right? I can give it an initial velocity towards the surface of the Earth. So when I throw an object down, I'm giving it an initial velocity. Right? So this object is going to have an initial velocity. When it leaves my hand, it's going to have some v initial. That v initial is going to be negative. Our coordinate system has been defined so that towards the surface of the Earth is negative. So if I throw an object towards the Earth, I'm giving it an initial velocity that's negative. Take that same object and drop it. If I drop it, when it leaves my hand, I'm going to say it has an initial velocity of 0. Right? So when I throw something towards the Earth, its initial velocity is going to be negative. Maybe it'll be given to me in the problem. Maybe I'll have to solve it. I don't know. But if I drop an object, its initial velocity is going to be 0. Acceleration will be 9.8 meters per second squared in the negative y direction. All right. So again, you can flip the coordinate system. I personally don't recommend it. I still like to say down is negative, but I'll show you again. I'll show you how I modify the kinematics equations to accommodate for that. So we'll start with the first example, right? Case 1, an object thrown towards the Earth. All right. So you're out. Your arm is hanging out of a window, right? You're 2.5 meters above the ground, right? You're 2.5 meters above the sidewalk, and you throw a baseball with an initial velocity of 2 meters per second. All right, that's 2 meters per second towards the earth. So when I write out what my V initial is, I'm going to give that a negative sign, right? 2 meters per second downward. What we're looking for is the velocity of the ball. So we're looking for a V final. We're looking for the velocity ball when it hits the sidewalk. Now, I want to take a moment because this happens very often too. The instant that ball hits the sidewalk, a lot of people will say the velocity is 0. Well, yeah, that makes sense, right? As soon as that ball strikes the sidewalk, it does come to a stop. Okay, but for the future, when we're talking about when an object strikes something, right, like it strikes the surface of the earth or hits the ground or something like that, we're going to talk about the velocity the instant before it hits the sidewalk, right? So we want to know how fast the object is going when it hits the sidewalk, right? Not when it actually comes in contact and comes to a stop and then bounces off, whatever it ends up doing afterwards. So we're looking for a final velocity. We can't assume that that's 0. So watch out for that. I see a lot of people, if they don't know what the final velocity is of an object when it hits the ground, they'll say it's 0, right? And that'll kind of help them solve the problem. But that's incorrect. So make sure we're looking out for that. So what do I have? I've got an initial velocity. I've got an initial velocity of negative 2 meters per second. Here's my picture. I'm still using the same problem-solving process that I used for the first couple examples. So I've got a negative initial velocity, 2 meters per second, in the y direction. I'm looking for the final velocity when it strikes the sidewalk. Again, it's not 0. It's got to hit it with some speed v. So that's what I'm looking for, just before it hits the sidewalk. Acceleration is g. Alright, so here's how I handle this. Acceleration is g, but it's in the negative y direction. Okay, so what I'm going to do is, instead of substituting a negative sign in, I know it's negative, so instead of substituting a negative sign in, the negative sign just represents the vector property of the acceleration vector. I'm going to modify my kinematics equation, so when I see g, I'm just going to substitute 9.8 meters per second squared in there. Okay, my equation is going to have the negative sign already put in there and taken care of. So I don't have a time, but I am given the initial position and the final position of the ball. You're 2.5 meters above the sidewalk. So what I'm going to say, my convention is the ground, by default, the ground is always y equals 0. Okay, so you can make it, you could switch it to where this initial position is 0. This is some negative displacement, right? What I like to do is, wherever the lowest point of the object is going to be at the end of the problem, 99% of the time it's the ground. Okay. Sometimes you'll see cases where somebody is on the ground and they're throwing an object up onto a building. But most of the time we'll have an object up top, right, some height from the earth, its final position. I like to call it 0. So that means you are some positive position above your origin, right, the ground. So y initial in this case is positive 2.5 meters. Y final is 0 meters. Whether you pick this to be 0 or you pick some height to be 0, you'll always get a negative displacement in this type of problem, because y final is 0 meters, y initial is 2.5 meters. You get a negative displacement. So that makes sense. An object is falling, right? It's traveling in the negative y direction. It's falling towards the surface of the earth, so its displacement is negative. All right. If you made this 0, you would have to make this negative 2.5. So you'd have negative 2.5 minus 0. You'd still get a negative displacement. I like this way personally, but if you flip them, you'll still get the same displacement. So we've got a displacement, an initial velocity Free fall problems will always have the acceleration. It's the acceleration due to gravity. So I look back at my kinematics equations. This kind of looks like one. Kind of looks like one of those kinematics equations. I'll tell you what I did to modify it for free fall. So the first thing I did was I gave my velocity vectors their subscripts, right? Gave them v final in the y, v initial in the y. Because later in chapter 3 we're going to talk about two-dimensional kinematics. We're going to combine horizontal and vertical motion. So this is a good habit to get into. Also, replace my delta x with a delta y. We're talking about displacement in the y direction, so my notation changes to reflect that. So this is normally v initial squared y plus 2a delta x in our traditional kinematics equation. What I did was I replaced a with g because we're in free fall. And I took this plus sign and I made it a minus sign. Why did I do that? Again, this is my preference. I like to change this to a negative sign. And then for g, because g, the magnitude of g is just 9.8 meters per second squared, I'm just going to plug the value of g in here. Okay. This negative sign represents the vector property of the acceleration due to gravity. So I make this sign negative and I plug positive g in for the acceleration. Now if this doesn't really sit well with you, you can leave this positive, leave this negative sign positive, like the old kinematics equation, and then substitute a negative 9.8 meters per second squared here. The point is, make sure you're not doing both. You should be doing one or the other. This negative sign is simply saying that acceleration is in the negative y direction. So you can do one of two things. Make this negative, plug positive g in for your acceleration, or keep this positive, substitute a negative 9.8 meters per second squared in for acceleration. Okay. So make sure you do one of those things, but don't do both. So I've got a new kinematics equation. It's been modified for free fall, but I still use the same process. I'm solving for v final y. Take the square root of both sides. I've got an expression for v final y. Okay. So I forgot my back in the high school days, right? You take, what's the square root of 9? Everybody says 3. All right, but it's plus or minus 3. Okay. So when I take the square root of this side, it's plus or minus. So that means I've got two possible velocity values. I'll show you how we decide which one of these signs we're going to use. So I substitute my values in, negative 2 meters per second for initial velocity. I've got that negative sign already changed. I'm going to plug a positive g in for the acceleration, and then my displacement is negative. So one way to make sure that you're doing this right, see this here, right, the negative sign and then the positive g. Sometimes this term, if this term ends up negative and then it's larger than this one, you'll get an undefined, right? This is what we called the discriminant, right? I think it was called the discriminant of a quadratic or something like that. So it looks a lot like that term under the square root in a quadratic formula. So you would get something that's undefined. So that will, your calculator yells at you, gives you an error or something like that. You got a pretty good idea that you maybe put two negative signs in here. Okay. So I'm going to evaluate what's under the radical. This term actually ends up being positive, right? I've got a negative displacement. I've got a negative sign here. This term will be positive, so I won't have to worry about any negative signs under the square root. Got plus or minus root 53. Root 53, I'm in meters squared per second squared. The square root of those units are meters per second. Which one of these signs do I pick? I've got 7.3 meters per second. I'm going to pick the negative sign. I'm going to pick the negative sign. Why? Because I know that this displacement is in the negative y direction. The acceleration is negative. And so when this ball strikes the ground, it's going to have a velocity in the negative y direction. So I give that a negative sign. Give that a negative sign. That's how I decide which one of these to pick. Okay. Alright, first nice example, scenario 1, object thrown downward, kinematics, I modified it. to reflect my free fall problem. Okay, so I've got another example of well, this is the second case. This is a second case. We just did an example where an object was thrown downward. This example of free fall problem is an object being dropped. Right, so we've got a construction worker on a scaffold. So this tells me that the initial velocity of the object is going to be 0 meters per second. So again, we're looking for the final velocity, but now we have a time interval, right? We know how much time the object is in the air, so we're being asked for two things. The velocity of the brick after a time interval. I don't know if it's hit the ground or not, doesn't really matter. So I have how long it's in the air, and then how far the brick falls. So I'm looking for the displacement of the brick, and I'm looking for the velocity 4 seconds after it's dropped. So I've got another picture. It's dropped, right? So it doesn't have an initial velocity. I've got a time interval of 4 seconds. Again, the acceleration is 9.8 meters per squared in the negative y direction. So instead of a displacement, which is what I'll be asked to solve for the second part, instead of a displacement, I've got a time. So this looks like the equation that is going to be useful here. My initial velocity is 0. That term goes away. Again, I modified this kinematics equation, right? This used to be v final equals v initial plus at. I modified it to resemble a free fall problem. So I replace a with g. The sign in front of the term that contains the acceleration, I changed the value, right? I make that negative. So this is going to be negative. Time is a scalar, it's positive. That's very nice because I'm going to get a final velocity that's negative. Negative 9.8 meters per second squared times 4 seconds. I've got a velocity 4 seconds later of 39.2 meters per second. Now I need the displacement. I've got everything that I need to use any one of the kinematics equations that I want. Right? My goal here is I want to save time, and so if I can avoid algebra, I would. So there are two equations that have that are already expressions for displacement, right? They already have like delta x equals something, right? So I picked the one that doesn't look like a quadratic because it's got fewer terms. The calculation is going to be a little bit easier. You can pick the delta y equals v initial t plus 1/2 at squared. I'm going to use that later on, and I'll show you how I modify that one too. But this one's just looks a little easier to handle. I found the final velocity. Right? I have the initial velocity, which is 0. So I can substitute those values in, substitute my time in. So I've got 0 plus a negative 39.2 meters per second. Don't forget this final velocity is negative. It's a vector pointing in the negative y direction. 4 seconds is still my time interval. So I calculate that, and I get a displacement of negative 78.4 meters. Okay. Again, either one of these would be okay for you to use to solve for the displacement, because we've got the time, we've got the two velocities, we've got acceleration. So these are how I modified the other two kinematics equations. Everywhere I see a delta x, I replaced with a delta y, because it's a vertical displacement. Gave my velocity term some y subscripts. I mentioned how good of a habit that is, and I look up here and I forgot it myself. So I'm prone to forgetting some notation here or there. I try my best. Notice I don't have vector hats all over the place. But I give my velocity vector some y subscripts. I replace a with g. I replace a with g in this one. And the term that has a in it, I make a negative sign. Right? Notice I was talking about earlier, I replace a with g and then I make that term that contains a negative. And then what I'll do is if I use one of these problems, or one of these equations to solve the problem, I'll just substitute a positive 9.8 in for g, right? Because I'm already taking care of the fact that the acceleration is in the negative y direction with these signs. Okay, so again, be careful. This is how I like to do it. If you want to substitute negative 9.8 in here, negative 9.8 in here, just keep these positive. Okay. All right. Third case, we throw an object up in the air. Right? We're either on top of a building, maybe we're at the bottom of a cliff, and we want to throw something up onto some surface, right? Or maybe we just want to throw it up in the air and catch it. So there are some sub cases of this case sometimes. If I throw an object up in the air, it's still under the influence of gravity. The instant it leaves my hand, the instant it is launched, whatever the object may be, acceleration is still going to be g, and it's still going to be in the negative y direction. Right? That's what free fall is. Any object that's in the air is only subject to the influence of gravity. Right? So the second an object leaves my hand or is launched, this is the acceleration. So it's technically in free fall. Even though it's traveling up, right? Maybe I give it an initial velocity that's positive, right? If I throw something up in the air, I give it a positive initial velocity. It's still called an object in free fall. Okay. It's going to reach a maximum height, right? So we throw it up in the air, we give it an initial positive velocity, and then it starts to slow down, right? Because gravity's trying to pull it back down to the earth. So it gets to a certain position, right? And it's max height, and it's going to turn around, right? It's going to slow down, it's going to come to a stop, and then it's going to start to fall back down. And it's going to speed up in the negative y direction, right? So when you throw it up in the air, it slows down, comes to a stop, changes direction, and then falls back down. If you're taking lab, this is kind of the nature of the second part of experiment 1. Okay, so you're asked to answer some questions about an object that's in the air, right, or accelerating under the influence of gravity. Okay, so check those graphs out in experiment 1. That'll help you kind of visualize this situation. Sometimes you'll be asked for max height, so we'll handle that situation too. So there's a sub case of this situation that we'll handle later, where the path of the object is symmetric. Okay, so if I launch something from the ground and then it returns to the ground, it's returning back to its initial position. So if I launch something from the ground and it hits the ground, that entire duration of motion is what we call it symmetric, because it's actually shaped like a parabola when we graph it. But the displacement is 0, right? Delta y is going to be 0 because it starts at the ground, ends on the ground. So the total displacement is 0. The time it takes for the object to get to its max height is the time it takes for the object to come back down to the ground. Okay, so that's an important property. Again, this is only if the object returns to its initial position. So this won't always be the case. But this is very useful for these types of problems. So the time it takes to get up to its max height is the time it takes to come back down. And then the final velocity when the object strikes the ground is equal in magnitude to the velocity with which it was launched, right? So it hits the ground at the same speed it left the ground, but it's negative, right? Because the vectors change direction, right? So the magnitude of the initial and the and final velocity are the same, but the direction is different. Okay, so that's also very useful. So here's a basic symmetric scenario 3 problem. Okay, I'm throwing a ball straight up in the air, giving it a velocity of 22.5 meters per second. So now it falls down, right? It goes up, reaches its max height, velocity is 0, comes back down, and I catch it, right? So I'm predicting that the velocity with which it hits my hand is going to be negative 22.5 meters per second. I'm catching it at the same position from which I threw it. So the velocity is going to be the same magnitude, different direction. It says, how high does the ball get? All right, that's my max height question. Max height question. And then how long is it in the air total? Sometimes I'll refer to that as like total hang time or something like that, right? Total time that the ball is in the air. So I'm looking for the total time the ball is in the air, and then its max height. Its max height. So I know it's got an initial velocity, 22 meters per second. I know it's in free fall. The acceleration is g in the negative y direction. And so I'm going to write all that stuff down. So here's a little picture. This is the starting point. This is when I launched the tennis ball. This is when it gets to max height. Right? So I'm drawing it at the bottom of its path. I'm drawing it at max height. And then I'm drawing it down here, right? I'm making the prediction. It's symmetric. So I know that this speed is the same as this speed, opposite direction. So this is how I handled it. I found the hang time first. Right? I found the total hang time first. And the reason I did that is because I know, based on the symmetry of the problem, I've got V final and V initial. Right? So this is kind of my shortcut here. This only works for a symmetric free fall problem. I know V final is negative 22.5. I was given V initial. I know the acceleration is due to gravity. So I'm going to use this. I'm going to use this right here, and this is going to tell me the time. Right? This is going to tell me the total time. This equation doesn't care that you started going in this direction and then you came back down, you changed direction up here, you had a max height. This equation is saying, what's your initial velocity? Good. What's your final velocity? Good. Here's the acceleration. I'm going to tell you the total time that that ball goes from this velocity to that velocity. Okay, so this is going to tell me the total time the ball's up in the air. So a little algebra, subtract V initial y from both sides. Don't forget, because I actually did when I was doing the solution, okay, happens to everyone, don't forget that when I'm subtracting this, that negative sign survives, right? You see how I handled this again, right? I got my subscripts, I got acceleration, I changed it to g, I made the term negative because acceleration is negative. And when you subtract, don't forget that that negative sign is still over here, okay? So I've got my change in velocity over here. It's equal to negative gt. Divide both sides by negative g and substitute my values. Don't forget V final is negative minus a positive V initial. Alright, so I'm going to get a negative term in the numerator, negative term in the denominator, which is good because I'm looking for time. It's a scalar. It's got to be positive. Alright, so if you forget this negative sign, you'll get a negative sign in the top, positive sign on the bottom, and you'll get a negative time. So hopefully you'll be able to catch your mistake if you forget where that sign went. So I found total hang time first, and then I know since it's a symmetric problem, I took this hang time and I divided it by 2, and that's the time it takes to get to its max height. Okay. Again, the two assumptions I can only make for symmetric free fall is the relationship between the velocities and the relationship between time up and time down. Okay. So I'm taking this. Okay, this is the time it takes to get up. I'm looking for the max height, how high the ball gets. So I'm going to call my displacement in the y direction. You'll see it written as like h max sometimes. Okay, you see it as h max. So what I did was I said v initial y was 22.5 meters per second. The final velocity, right? The final velocity now is the velocity it has up here, right? Because I'm not concerned with the motion all the way up and all the way down. I'm just concerned with the motion all the way up. So v initial is 22.5 meters per second. My v final for this part of the problem is 0 meters per second because I'm worried about max height. The time I use here is a different time, right? The time it takes to get up to max height, not this total time. I divided that by 2 and got 2.3 seconds to get the time it takes to get to max height. Plug everything in, and I've got a max height of 25.9 meters. Okay. So there's another way of doing this problem. You could do it in the order in which the problems were asked. So I used this equation because I'm looking for the displacement. Right? I'm looking for the displacement of the object as it gets to its max height. Okay. So this h max is going to replace delta y. All right. Modified my equation, got my g, got my negative, got my velocities. But now I set this problem up so that I'm only concerned with the first half of the object's path. I'm only concerned with from here to when it gets up to max height. So that means I'm going to use 0 meters per second. I'm going to use this V2 that I called it. I'm going to use 0 meters per second here for V final because I'm looking for H max. I know V initial. I know my acceleration due to gravity. So I can solve for H max. I can solve for my max height. So subtract V initial y squared from both sides. This negative sign survives. Don't forget when you're using this equation, those squareds tend to disappear sometimes. So make sure you keep track of them. Negative sign stays over here. I replace delta y with H max. That's what I'm looking for. Divide both sides by negative 2g. Get H max by itself. Okay, so I get this nice expression for H max. Substitute everything in. 0, 22.5 for V initial. The negative sign, 2, 9.8 meters per second squared. So again, I'm getting a negative sign here. Here's another thing too. This minus V initial y squared, this negative sign is not contained in this term. Okay, so you see what I'm doing here? I'm substituting positive 22.5, squaring that. That negative sign survives. Okay, so don't square that negative sign. Alright, so I get a positive vertical displacement, 25.9 meters. Is that the same thing I got in option 1? Yes, it is. Alright, so I still get the same max height by picking a final velocity of 0. Right, so this equation knows that I'm talking about max height. Okay, when I say final velocity 0. Now that I know H max, I'm going to use this equation. So I'm kind of working backwards. I'm going to use this equation. Now that I know H max, I'm going to use it to solve for the time it takes to get up to max height. And then what I'm going to do with that T2 is I'm going to double it. And once I find the time it takes to get up to the max height, I know it takes the same amount of time to come back down. So whatever this T2 ends up being, I'm just going to double it and I'll get the total hang time. So let's solve for T2. Multiply both sides by this 2. Get rid of the 1/2 on the right side. Divide both sides by this whole term right here in parentheses, right? V2 plus VIY. So I'm getting T2 by itself. Okay. So I got a nice expression for T2, which is 2 times my max height over the sum of the velocities. It's still 0 here, right? Because I'm just finding the time it takes to get to max height, not the total hang time. Okay. So I plug my values in. I get 2.3 seconds. Guess what that is? The 2.3 seconds I found here when I split my total hang time in half. So I'm in good shape. Right? I'm solving it in a different order, but I'm still getting the same values. Double that number and you will get 4.6, 4.59 seconds for your total hang time. Okay. Try this. Okay, try this on your own. Use this equation right here. Use this equation. It's a quadratic. At first glance, I'm not really interested in using it. But this delta y is 0. If I set this delta y to 0, I want you to try this. Set this delta y equal to 0. You know everything in here but the time. So try and solve for the time. It might come out a little bit familiar. I think we have a problem similar to this in the first part of chapter 2. Okay. So give that a try, and that'll give you the total time the ball's in the air, right? Because delta y is 0, you can use this to solve for time. Find the total hang time, and then you'll be here, and then you can do this again to find your max height. Okay. A lot of different ways to solve our problems. Okay, so I'm going to pause and see how long this thing is, and then maybe I'll upload it and split it into 2 parts. Hope everything's going okay. Hope the videos are working. Like I said, email me, get in touch if you have any issues, okay? All right.